Welcome back everyone to the aromatic substitution reaction chapter. Today we are going to be talking about what happens when we put multiple substituents on an aromatic ring. What happens to the directing effects? Alrighty, so let's get into it here. I want to start with an example. I have a phenol with a methyl group in the para position to that hydroxy group, and I want you to predict the products. Alright, so before we draw the products, let's point out what these groups really are. We know that this hydroxide group is activator because it can donate one of these lone pairs, and that means it's going to be ortho-para directing, right? Ortho means one away. So we know that this hydroxy group wants to direct to here or here. A methyl group is also activating, meaning it's going to go to the either the para position or the ortho position. So it's going to want to go here or here. So we have a slight problem. We have two activating groups that want to go to all other carbons that don't have a substituent. But let's see why it's going to pick one way or the other. So when we predict the products here, we're going to get this molecule. And I'm going to draw fun little colored pi electrons because I think chemistry needs to be more fun. It's losing some of its charm because everyone, all your professors, they try and make it terrible. They try and torture you. Here, we don't torture. We're fun and colorful and playful. Okay, so our NO2 group is going to attach right here. It could also attach over here as well. So we'll draw like, I don't know, also could be here. I'll just point an arrow so you don't forget. But why is that? Alrighty, remember how in the last episode we looked at that spectrum? There's strong activators, there's mild activators, there's weak activators. Well, we know that hydroxide, the hydroxy group here, is a strong activator. It's strong. And that basically means, okay, it can donate electrons and it doesn't have anything else competing with it. It's not weak, it's strong. Okay? And the methyl group here can only be an activator through hyperconjugation, and that means it's weak. So when we compare the two, we know that the stronger one is probably going to win here, and that's exactly what happens. Notice how activators are ortho-para, but both of the para positions for both substituents are taken. So we're not going to get any weird competition with the para position. That only leaves the ortho position to be competed with. Now, when we compare strong to weak, of course the strong is going to win, and it's going to favor positioning itself on this carbon and this carbon here. And it's not going to select for what the weak directing group is going to be, which is that group and that group. Alrighty, so we looked at the power of our activating or deactivating groups as kind of that deciding factor of where it's going to go. I want to also look at another effect here that can occur when you have multiple substituents and you need to predict where something's going to go. Okay, so we have two alkyl groups here, and I'm going to do a nitration. I just spelled it NITR ... Couldn't fit it, and I didn't want to spell the reagents because I'm lazy. So just know that we're doing a nitration. Remember adding an NO2 group. So I want you to try and predict the products here. Okie dokie. So we know that these groups here are our alkyl groups. These are weak activators, meaning that they're ortho-para directing. Para position is taken up, and we know that it's going to direct our NO2 group to the ortho positions. And again, we have that competition. This group competing with this side, and this one competing with this side. We have two of the same, right? So in the initial part of this video, we looked at, okay, two differing groups of strengths. But this here, we have the same strength. They're both alkyl groups. So what is the difference here? That's going to be steric hindrance. Oh no, it's coming back to haunt us, guys. I didn't think this day would come. This is the reason I would get my problems wrong in organic chemistry. One, and it's coming back to haunt us now, steric hindrance, and then I'm going to draw a shocked face like, oh no, everybody run. Kind of looks like a cat. I'm going to just make this into a cat. How cute, guys. See, on this channel, this is the only channel you'll find that has cute stuff like this, where we draw cute little kitty cats. And I'm going to give that beautiful little kitty cat blue eyes. Oh, now it just looks demented. Oh, goodness. Okay, back to what I was saying. Steric hindrance is the main deciding factor. So we know that it's going to go in one of these ortho positions relative to one of the alkyl groups. Let's see our major product. It might surprise you. I don't really think so if you use logic and reasoning here. But it's okay if you didn't get it, because I'm going to tell you. So you'd expect, let's just assume mono substitution, only adding one group. So we might get this product, but, and I'm going to draw this one in hellish orange, because I'm so cool. Look at me, guys. All the ladies want me, I promise. Okay. And then we have this. We have two products that we can choose from. Now, if I asked you which one's going to be minor and which one's going to be major, what would you say? Well, hopefully you'll say that this one is major. And if you didn't, again, that's fine. We're going to figure out why this is major and this is minor. Alrighty, so this product here, our major product, notice how the steric interaction, there is some steric interaction between this alkyl group here and this NO2 group here, right? So there's some steric interaction, right? But over here, on the minor product side, we have a very bulky propyl group, right? We know that this here is just one little itty-bitty carbon and his little hydrogen friends. Here it's carbon, 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 and then there's those itty-bitty hydrogens on the end. That's a pretty fat group compared to just a simple little methyl group, right? So there's some big steric interactions. I'll draw it in hellish red. There's some big steric interaction. It is not happy right there, that NO2 group. But again, that NO2 group's kind of fat itself. Oxygen atom, two oxygen atoms and a nitrogen atom, bigger than carbon. Actually, no. Oh my goodness, I'm selling. Still, bigger interactions. Anyways. Okay. Disregarding the fact that I just called the atomic radius of nitrogen and oxygen bigger than carbon, which is pretty stupid. I want to now just summarize everything that we've learned, because I kind of went a little fast with this lesson. I want to slow things down and remember one thing when deciding. So we have a problem, and our problem, this is a problem-solving technique that I do when I need to determine. We have a problem. What's that problem? That problem is multiple substituents for an aromatic reaction. Multiple substituents for an aromatic reaction. So, what is the first thing we should look at? The first step is look at strength. Okay. And if you are ever given a test problem for this, you will never be given similar strength. Like, if you will never be given two strong groups that are different from each other and be asked to determine which is the major. The difference is small, but if there is still a difference, right? Because, you know, one's going to be stronger than the other, but you're not expected to know directly, you know, just off of two very similar strength, either deactivators or activators, right? So look at the strength, compare that, make your choice, right? If that doesn't help, look at steric hindrance, and that will definitely help you find the answer. And if there's no answer there, then there's most likely no selectivity, no directing from those multiple substituents, and it will just follow normal rules, right? So thank you guys for watching. That was multiple substituents, what to do, how to solve them. Hopefully you guys enjoyed that episode there. I hope you have a wonderful day, and make sure to stay tuned. We're going to have some extension. This was the last video of the official course, but I want to add on a few other concepts in the textbook that are on the lateral half, very small concepts. So thank you guys very much.